For centuries, we thought machines followed our rules. We build them, we control them. Yet, we were wrong. A chip the size of a palm, cooled to absolute zero, shattered this belief. When a 53-qubit processor named Sycamore was turned on, the impossible happened. In just 3 minutes, it finished a problem that would take the world's most powerful supercomputer 10,000 years to solve. Because those 53 qubits held more than 9 quadrillion possibilities at once, a state that physically should not have existed. But the real shock isn't this staggering speed, it's the secret this machine whispers, the possibility that reality splits into infinite branches at every single moment. If the idea that there's only one solid reality for you is no longer enough, then subscribe to this channel and like the video. Because what you are about to see could change how you see the universe forever. Let's begin. For years, we summarized the future of computers in a single word: speed, smaller transistors, denser circuits, and ever-increasing processing power. Because the logic was simple: to solve a problem faster, you needed a faster machine. But this picture had a limit, a wall drawn by the most fundamental laws of physics. That is why scientists began searching for a way not to break through that wall, but to go around it. And in October of 2019, they showed the entire world what that path looked like. This was the moment that everything changed. Because, in a Google lab in Santa Barbara, a machine was turned on, standing inside a room colder than even deep space. From the outside, it looked like a tall, layered metal cylinder covered in cables. But that wasn't the important object. The important thing was a tiny chip, held at a temperature near absolute zero. Its name was Sycamore, and it was given a task that wasn't very useful in a practical sense. It wasn't designing a drug, it wasn't predicting a storm, it wasn't breaking a password. Its job was a benchmark test, called random circuit sampling. This test was chosen specifically because it is extremely easy for a quantum device to perform in its native language, and incredibly difficult for a classical computer to directly imitate. When the results came in, the world held its breath. Sycamore completed this task in a little over 3 minutes. According to Google's report, the best classical supercomputer at the time would have needed about 10,000 years to produce the same result. But that wasn't the real shock. IBM soon objected. They argued that with better classical techniques and enough storage, this time could be reduced to a few days. However, this debate couldn't overshadow the main event. Because the issue wasn't a few days or 10,000 years. The issue was that a tiny processor of 53 working quantum bits had entered a region where classical imitation becomes massively expensive. And the reason for this was not an ordinary speed increase. The reason was the very language that makes up quantum information. The computer you know speaks in bits. A bit is definite. It is either a 0 or a 1. It's like a light switch, either on or off. There is no other possibility. That's why we must understand the fundamental unit used by this new machine. Because it uses something completely different, called a qubit. A qubit, before it's measured, is not in a definite state. Its state is represented by mathematical quantities called probability amplitudes. These amplitudes can combine, cancel each other out, and change in ways that ordinary bits never could. Even a single qubit carries richer information than a single switch. But the real vertigo begins when you bring them together. 2 qubits can be described as a joint quantum state. When more qubits are added, and especially when they become entangled with each other, the description of this state grows at a terrifying rate. The 53 qubits Sycamore had require a state space with over 9 quadrillion fundamental configurations. Think about that number for a moment, a 9 with 15 zeros after it. Therefore, to understand the true power of this machine, we must scale it up even further. Imagine just 300 well-controlled qubits. The state description of these 300 qubits would have more fundamental configurations than there are atoms in the observable universe. This is what gives a disturbing clue about reality itself. But we must be very careful here. This statement doesn't mean the machine stores all these possibilities like a classical record. It also doesn't mean it has a bigger memory than a conventional machine. The real point is much more subtle and much more interesting. A quantum computer does not keep a classical list of every possibility. It is not faster because it quickly scans a long list. It is different. Because it allows a physical state to evolve in a space of possibilities that classical computation struggles to represent. This is why the Sycamore result felt so important. It was a narrow victory. It was carefully chosen and not directly useful. But it showed that quantum hardware could cross a threshold where classical copying becomes profoundly inefficient. For decades, quantum computing had existed partly as a promise and partly as a problem. Physicists knew the equations, mathematicians had designed algorithms that could, in principle, outperform classical methods, and engineers had learned how to cool, isolate, and control small quantum systems. Yet, the central challenge always remained the same. Qubits are fragile. They lose their coherence when information leaks into the surrounding world. Gates are imperfect. Measurements are noisy. So, a useful quantum computer cannot be built just by adding more qubits, because every added qubit also introduces new avenues for error. What the field needed was proof that these machines could scale without drowning in their own noise, and after Sycamore, that proof began to arrive. But all this progress was exposing a much more fundamental problem waiting at the door. If these machines derive their power from such a fragile foundation, what was keeping them alive? What was protecting them from the universe itself, which tries to make everything classical and boring at every moment? Because running these machines is not just an engineering problem, it is a battle against reality itself. And on the front line of this battle, there was an invisible enemy trying to destroy all quantum effects, an enemy so powerful that, and the name of this enemy is decoherence. Schrödinger's cat did not enter physics as a mystery mascot, but as an objection. Because, in 1935, Erwin Schrödinger was trying to show that the language around quantum mechanics had become too careless. The equations said that a radioactive atom could be described as both decayed and not decayed just before measurement. Schrödinger carried this logic into a closed box. If the atom decayed, it would break a vial of poison and the cat would die. If the atom did not decay, the cat would live. Therefore, if the atom existed in both possibilities at once, must the cat also be both alive and dead before the box was opened? Schrödinger intended this as a warning. But the problem did not go away, because the atoms that make up a cat, a table, or a measuring device are also quantum systems. There is no known boundary where the equations simply stop. Therefore, the reason large objects do not appear in visible superpositions is not that they are exempt from quantum physics. It is that the quantum possibilities become unusable almost instantly, through a process called decoherence. This quiet concept transforms the cat from a paradox into a working description of why the everyday world appears stable. Decoherence begins when a quantum system interacts with its environment. A photon bounces off it, an air molecule touches it, heat flows through it. Every interaction carries away information about the system's state. This information does not need to be read by a human mind. It does not need a conscious observer, it just needs to spread into the surrounding world. Once it spreads, the different components of the quantum state become entangled with different states of the environment, and they can no longer practically interfere with each other. The system appears as if it has chosen a single outcome. But what's crucial is the speed of this process. A cat is too big, too warm, and too complex to remain isolated. It radiates heat from its body. Its cells metabolize, its surface scatters light. Long before anyone opened the box, the cat's state would have become entangled with a vast environment of particles, fields, and internal records. That famous alive and dead superposition would become inaccessible almost instantly. This is why a coffee cup sits on the table. It is fully quantum at the level of its atoms, but it is stable at the level of everyday observation. Because light, air, heat, and gravity are constantly linking it to the rest of the room. The cup is not classical because it escapes quantum mechanics. It appears classical because its alternatives decohere faster than an ordinary observation can notice. This explains why quantum computer engineers go to such extremes. Because building a quantum computer is about reversing this everyday situation as much as engineering allows. They try to keep the qubits quiet, isolated, and controllable. Their goal is not to make a cat both alive and dead. The goal is to keep a small, carefully designed quantum system coherent for long enough for the amplitudes to evolve in a useful way. This is why quantum processors are placed in dilution refrigerators, vacuum chambers, electromagnetic shields, and vibration-controlled systems. The cold is not decorative, it reduces thermal motion. The shields are not excessive, they prevent stray fields from corrupting the state. A qubit is powerful only as long as it remains coherent. If the environment learns too much about it too soon, the computation loses the feature that makes it quantum, and the machine becomes a noisy classical device with fragile parts. This is why error correction is so central. Useful machines of the future will not rely on perfect physical qubits. Therefore, they will use many imperfect qubits to encode a smaller number of more reliable, logical qubits. The idea is not to directly copy unknown quantum states, because quantum mechanics forbids it. Instead, error correction spreads the information across entangled systems, so that specific errors can be detected and corrected without measuring the protected quantum information itself. This is one of the most subtle achievements in the field. A quantum computer is a box that must, in fact, remain properly closed. The computation inside must not be disturbed by uncontrolled observation, but it must not be cut off from control either. Engineers have to interact with the system without learning the wrong information too early. They have to shape the state without forcing it to settle. They have to delay decoherence without eliminating all communication. Because a machine that cannot be prepared or read is useless. So a working processor lives between two failures. Too much isolation makes it unreachable. Too much contact destroys coherence. But all these efforts point to a much larger and more unsettling idea. If reality is constantly forcing quantum states into a single outcome, then what happens to those other possibilities that existed before the measurement? Are they just a mathematical tool or something more? And just then, in the 1950s, a graduate student at Princeton got stuck on this question, because for Hugh Everett, this silence was too deep to ignore. Instead of asking what collapses the wave function, he asked whether the collapse had to exist at all, and the answer he developed was simple in form and radical in consequence. The wave function never collapses. It always evolves according to the normal quantum equations, because, according to Everett, when a measurement occurs, the measuring device, the environment, and the observer become entangled with the system being measured. Every possible outcome continues to exist in the total quantum description, but the observers inside each outcome only experience the branch they belong to. In one branch, a detector registers one result. In another branch, an equally real detector registers another result. The observer is not outside the process. The observer is part of the physical system that is branching. Everett called this the relative state formulation. It later became widely known as the many worlds interpretation. But this name can be misleading if it makes you think of separate planets floating somewhere in space. The idea is not that distant copies of the universe are arranged like islands. The idea is that the universal wave function contains different branches that no longer interfere in an ordinary way after decoherence separates them. Therefore, for Everett, this approach had a powerful advantage. It did not add a special collapse rule. It did not divide reality into quantum systems on one hand and classical observers on the other. It treated the entire universe as quantum, including instruments, labs, and human observers. But while this made the theory cleaner in one sense, it made it even harder to accept emotionally and philosophically. The price of avoiding collapse was to accept that all outcomes described by the quantum state persist. Everett defended his work as a simple reading of the mathematics. But the physics community around him was not ready to follow. Niels Bohr and the Copenhagen school had shaped the dominant attitude toward quantum mechanics, and their approach put less emphasis on describing an underlying reality than on predicting what can be observed. Everett's thesis was not well received. He left academic physics and never gained the scientific recognition he deserved during his lifetime. But the later revival of his idea adds a quiet sadness to the story. A framework once seen as extravagant began to look to some physicists like the most economical interpretation of the same equations everyone was already using. This shift did not happen at once. For years, many worlds remained a minority view. discussed by philosophers of physics and a small number of theorists more than it was embraced by the mainstream. What changed was not a single experiment that proved Everett right. What changed was the pressure that quantum information applied to the idea. As physicists began to treat information itself as a physical quantity, and as they began to ask what a quantum computer would actually be doing, it became harder to dismiss Everett's view as merely extravagant. Because a quantum computer does not just reveal one outcome of an isolated quantum event. It deliberately prepares many qubits in a joint state, allows the amplitudes to evolve through a carefully designed sequence, and then uses interference to make some outcomes more probable than others. Therefore, for David Deutsch, this was not just a useful mathematical description. This was evidence of the literal structure of reality. Deutsch, working at Oxford, took Everett's proposal seriously and carried it to the foundations of computation. In 1985, he published a paper defining a universal quantum computer based not on ordinary bits, but on the allowed operations of quantum theory. This paper gave the field a theoretical foundation. Deutsch argued that when a quantum computer evaluates a problem, the different components of the computation correspond to activity in different branches of the multiverse. The final interference pattern then brought information from these branches to bear on the outcome observed in a single branch. This was a powerful claim, and it remains controversial. Many physicists use quantum computation without accepting Deutsch's interpretation. A researcher can use the standard mathematical machinery while remaining neutral about whether the branches are real worlds, useful terms in a calculation, or something else. Quantum hardware does not force every physicist to become an Everettian, but it does make the old measurement problem harder to ignore. The machine's advantage comes precisely from sustaining a quantum state that contains more structure than any comparable classical description could easily hold. It's fair to call this structure computation, but explaining what that structure is a deeper question. And Everett's legacy is not that this debate is over. His legacy is that a once rejected answer became relevant again, because modern machines behave as if the non-collapsing quantum state is not just a formal accounting, but an exploitable physical resource. And now comes the real shock, because this resource was not just in machines, but perhaps everywhere. And therefore, the silent quantum machinery of life does not look anything like laboratory processes. A leaf is not a refrigerated chip. A bird is not a device isolated from its environment. A cell is warm, wet, crowded, and constantly active. This situation led biologists and physicists for many years to assume that useful quantum coherence could not survive there. Because the logic seemed sound. The easiest way to preserve quantum effects is when a system is cold, isolated, and carefully controlled. Living matter is almost the exact opposite. Proteins bend and vibrate. Water molecules collide with everything around them. Chemical reactions generate heat. In such an environment, delicate superpositions should be destroyed almost instantly by decoherence. But then, researchers looked closer at photosynthesis. Because the first stage of photosynthesis has to transport the energy from absorbed sunlight through a structure of pigment molecules to a reaction center where that energy can be converted into chemical form. Classical intuition suggests the energy would hop from one molecule to the next, losing some of along the way. Yet, many photosynthetic systems move the energy with remarkable efficiency. In 2007, experiments using ultra-fast laser methods on photosynthetic bacteria found evidence that the energy transfer involved coherent quantum behavior, lasting just long enough to influence the route through the molecular structure. The energy did not seem to be blindly wandering from one place to another. It behaved like a quantum excitation distributed over several possible paths, where the structure of the protein helped to guide it toward the reaction center. We must be careful here. A leaf is not running a general-purpose quantum algorithm. It is not thinking, choosing, or solving problems in the human sense. Therefore, the more precise claim is this. Some biological systems seem to preserve quantum coherence for just long enough to improve a specific physical task. In photosynthesis, that task is energy transport, and the surrounding protein does not just threaten coherence, it may also help to shape it and preserve it for the brief time it is needed. This is an important shift. In artificial machines, Engineers go to enormous effort to eliminate noise. In living systems, evolution may sometimes use a controlled amount of environmental motion to help the process, rather than just destroy it. But this was only the beginning, because an even more impossible-seeming discovery came from migratory birds. Many species can sense the Earth's magnetic field and use it during long journeys. This field is weak, much weaker than many magnetic disturbances found in ordinary environments. So, explaining the biological mechanism was difficult. A leading proposal involves molecules called cryptochromes, found in the eyes of birds and other animals. When light interacts with these molecules, it can create radical pairs, molecules with unpaired electrons. The spins of these electrons can become correlated in a quantum way. Their joint state can be influenced by the direction of the Earth's magnetic field, and this, in turn, can alter the chemical products that are formed. In this model, the animal does not sense magnetism like a compass needle spinning inside its skull. Instead, the quantum spin chemistry can slightly alter reactions in light-sensitive proteins, and the nervous system can interpret these changes as directional information. It doesn't matter that the bird contains a miniature quantum computer. What matters is that a quantum state sensitive to magnetic direction can leave a chemical trace, large enough for biology to use. Enzymes open a third window because enzymes are proteins that speed up chemical reactions. In many reactions, a particle like a proton or an electron has to move from one arrangement to another. Quantum mechanics allows another possibility, called tunneling. A particle can pass through a barrier in a way that has no simple classical equivalent. Evidence suggests that tunneling contributes to some enzyme reactions, making them faster or more efficient than they would be if the particles had to overcome the barriers in a purely classical way. This does not mean enzymes violate chemistry. It means that chemistry has been quantum all along, and enzymes may have been shaped to take advantage of that fact. The protein environment can precisely position atoms, adjust local electric fields, and create the conditions where tunneling becomes more probable. Photosynthesis, avian navigation, enzymes. All of these suggest that even though life is warm and noisy, quantum behavior is not impossible. But all this raises an unavoidable question. If life can use quantum mechanics at such fundamental levels, what about the mind itself? What if that most intimate, most indescribable quality of consciousness is actually an echo of the quantum world? Because if it is, then the most terrifying truth about reality was much closer than we thought. But how does it work? What is the real mechanism behind all this astonishing power? Now let's get technical and understand how the engine inside that cold room actually runs. Because what gives a quantum computer its power is actually interference. A qubit being in a superposition is not useful just because it has more than one possible value in its mathematical description. If the process ended there, a quantum computer would produce a confusing spread of possible answers, and a measurement would just pick one sample from this cloud. The real trick lies in orchestrating the evolution of the quantum state, so that the structure of the problem changes the probabilities of the outcomes. Some possible paths should be strengthened, while others should cancel each other out. Therefore, the final measurement should not be a random look at the mess. It should be a carefully prepared event, where the correct answer has been made much more likely to appear. This is the principle that turns quantum behavior into computation. It is also why quantum computers are not just parallel classical machines. They do not try every answer in separate ordinary lanes and then compare the results. They use amplitudes, the wave-like quantities that quantum theory assigns to possible states. These amplitudes can be positive, negative, or mathematically complex, and because of this, they can combine in ways that ordinary probabilities cannot. Ordinary probabilities just add up. Quantum amplitudes can add, subtract, rotate, and cancel each other out before a final probability is produced. The observable result emerges only after this hidden arithmetic has taken place. Richard Feynman understood the importance of this difference long before practical quantum computers existed. Because, in the early 1980s, he argued that simulating quantum systems with classical computers faced a fundamental obstacle. Even a small number of interacting quantum particles could require a classically overwhelming description. Because the particles do not behave like independent little objects with fixed properties. Their joint state contains correlations, alternatives, and phases that grow rapidly with each added component. Feynman's answer was clear. A system governed by quantum mechanics should be simulated by another system governed by quantum mechanics. Instead of forcing a classical computer to mimic the quantum world from the outside, a new kind of machine could let quantum physics perform the evolution itself. This meant that computation could be treated as a physical process, and the best machine for a problem might be one whose physical laws resemble the problem being solved. The double-slit experiment shows why interference is so profoundly important. When light or electrons pass through two narrow openings, the pattern that appears on a screen is not what would be expected from tiny particles simply choosing one opening or the other. It contains bright and dark bands where the amplitudes have reinforced, making detections likely, and where the amplitudes have cancelled, making detections rare or impossible. The point is not that the particle secretly chooses a familiar path. The quantum description contains alternatives whose amplitudes combine, waned, before an observed result emerges. Quantum computation takes this behavior and makes it programmable. The gates applied to the qubits change the amplitudes and phases of the quantum state. A well-designed algorithm uses these changes to make the wrong outputs interfere destructively, and the useful outputs interfere constructively. The machine does not know the answer in advance. It follows a sequence of allowed physical transformations. But, if the sequence is chosen correctly, the structure of the problem is translated into an interference pattern where the measurement is biased toward the answer. Therefore, there is a quieter but more precise way to describe this apparent weirdness. A quantum computer does not create the answer out of nothing. It reshapes the landscape of amplitudes until the measurement is more likely to reveal the answer. But one must be careful with the word easier. Quantum algorithms do not make every hard problem simple. Many tasks receive no known quantum advantage, others get only a limited speed up. The field is powerful partly because it is selective. It shows that certain mathematical structures are especially suited to interference. The most famous example is Shor's algorithm, introduced in the 1990s for factoring large numbers. It targets the practical difficulty on which many common public key encryption systems are based. Shor's algorithm reframes factoring as a problem of periodicity. A quantum computer can place many inputs into a superposition, evaluate the function coherently, and then use a quantum Fourier transform to reveal the period through interference. The machine is not checking possible factors one by one. It is using a structure allowed by the phase relationships between many possibilities to reveal the hidden repetition that leads to the factors. Therefore, a large fault-tolerant quantum computer would have serious consequences for cryptography. The danger does not come just from raw speed. It comes from a specific match between a problem used by cryptography and a quantum procedure that can efficiently extract its structure. Grover's algorithm, developed shortly after, shows a different kind of advantage. It applies to unstructured search, the goal of finding a marked item in data without a useful ordering. A classical search might need to inspect a number of items proportional to the size of the list. Grover's algorithm can reduce the required steps to roughly the square root of that size. This is not the overwhelming speedup that Shor's algorithm offers for factoring vertical bar, but it is broad. The algorithm repeatedly reflects the amplitudes so that the marked answer grows in probability, and the unmarked answers shrink. Each step is small. The repetition gives the marked state a larger share of the final measurement outcome. And again, the machine is not inspecting each entry in a familiar classical way. It is adjusting the amplitude so the desired result becomes increasingly favored. The lesson from both algorithms is that quantum computation is not general magic, but a controlled physical accounting with phases. Its power emerges when a problem can be encoded so that interference does a meaningful job. But that power is always hanging by a thread, because interference can only help if, and only if, coherence survives. If random noise scrambles the phases, the wrong answers may no longer cancel out, and the useful answers may no longer reinforce. And then, all that incredible computational power instantly turns into error. This is why every abstract advantage comes with a physical demand, and that demand requires building a wall against reality itself. And this wall is built with reality itself, because every qubit in a processor is surrounded by other matter, other fields, and other motion. This is why decoherence is not a side problem. It is the central pressure that all quantum hardware is designed to resist. The physicist most associated with clarifying this pressure is Wojciech Zurek, who worked at Los Alamos and developed the modern theory of decoherence. Zurek helped show that the environment is not a passive backdrop. It acts like a vast monitoring system, constantly becoming correlated with the state of physical objects. When a dust mote floats in the air, photons scatter off it, and air molecules collide with it. These interactions encode information about where the mote is. Many copies of this information proliferate into the room. Observers can then agree that the dust mote is in a single place. Nobody needs to disturb the mote directly. The environment has already carried the record. Therefore, Zurek later gave this idea the name quantum Darwinism, not because biology is involved, but because only certain stable properties of a quantum system survive repeated contact with the environment in a form that can be widely copied. These stable properties are sometimes called pointer states. They are the states that remain readable after the environment has done its work. This provides a practical explanation for the robustness of everyday experience. The world appears classical because the environment is constantly selecting and broadcasting the same kinds of information. Position, shape, and other robust properties become accessible to many observers. The delicate quantum phases do not. They are real in the equations, but not open to ordinary experience after being dispersed through countless correlations. In this sense, the classical world is not a separate layer added on top of quantum physics. It is the part of quantum physics that remains stable under relentless environmental contact. Therefore, a rock is not outside of quantum theory. A table is not outside of quantum theory. Their apparent definiteness comes from the speed and integrity with which information about them spreads into their surroundings. The bigger and hotter an object is, the more channels it has for leaking information. Heat, light, vibration, chemical motion, and internal complexity all work together to suppress visible superpositions. This is why daily life does not feel quantum, even though it is made of quantum objects. Experience is shaped by the states that survive environmental monitoring. Anything more delicate has already become inaccessible before awareness can form a record. This explains why superconducting machines are cooled to such extremes. The chip is cooled to a temperature just a tiny fraction of a degree above absolute zero. At such low temperatures, thermal noise subsides, and the circuits can enter superconducting states where electrical resistance vanishes. But the qubits are still not perfectly isolated. Their materials contain defects. The control lines can introduce noise. Neighboring qubits can disturb one another. So, engineers work not just on the qubits themselves, but on the entire environment around them. The refrigerator, the cables, the filters, the shields, the microwave pulses, and the software calibration all become part of the quantum machine. Trapped ion systems face the same enemy in a different form. Their qubits are single atoms, suspended in electromagnetic fields in an ultra-clean vacuum where stray gas molecules are rare. Lasers manipulate the internal atomic states with high precision. These systems can maintain coherence for longer than many superconducting devices. But they can be slower, and scaling them up presents other challenges. Neutral atom systems arrange atoms with light, using optical tweezers to arrange them in reconfigurable patterns. Photonic approaches try to build with light itself, using particles of light that travel well but are difficult to make interact in the controlled ways required for logic. Each architecture is different. Yet, each is a strategy for negotiating with decoherence. None can escape the environment entirely. Each tries to make it harder for the environment to steal the relevant information. This is where the word isolation can be misleading. A quantum computer is not simply sealed off. It must be insulated from noise and connected to control. It must be protected from accidental information leakage, while allowing for precise intentional operations. Too much isolation makes the qubits useless. Too much access makes them classical. The machine works only in the narrow middle ground, where a designed interaction can steer the state, and undesigned interactions are suppressed. This is one of the reasons why judging progress just from qubit count is difficult. More qubits do not automatically mean more power. A larger device with poor coherence, noisy gates, and weak connectivity can be less useful than a smaller one with cleaner control. The metrics that matter include error rates, coherence times, gate fidelity, and measurement reliability. But all of this is just the beginning of what's truly exciting, because these machines are not just a faster calculator. They offer a way to play with information at the most fundamental layer of the universe, and the rules of this game may make us question everything we thought we knew about space, time, and reality itself. Because these machines are not just an engineering marvel, they could be a doorway to one of the deepest secrets of the universe, a layer of information that lies beneath matter. And now comes the real miracle. Because, near the end of his life, John Archibald Wheeler began to describe reality in a way that seemed simple on the surface. Matter, he said, may not be the most fundamental ingredient of the universe. Energy may not be the most fundamental ingredient either. Beneath the particles, fields, and forces, there may be information. Wheeler compressed this idea into the phrase "it from bit," as meaning the things of the world may arise from more fundamental acts of distinction, from physical questions that have physical answers. This phrase can sound abstract, but it connects to a serious line of evidence in modern physics, because information does not just behave like a human label put on the world after the fact. It behaves like a physical thing. It can be stored, moved, preserved, erased, and paid for in energy. Therefore, in the early 1960s, Ralph Landauer argued that erasing a bit of information has a minimum energy cost. The amount is small, far beyond ordinary sensation, but it is not zero. Decades later, experiments with microscopic systems confirm this principle with increasing care. When information is erased, heat is released into the environment in a way that is consistent with Landauer's limit. This does not mean that ideas have weight in the everyday sense, or that memory behaves like a little object sitting inside the mind. It means something cleaner. Information is inseparable from physics. It is always carried by a physical state, and changing that state has consequences. This insight is crucial for quantum computation. Because qubits are not just delicate switches, they are physical carriers of information whose possible states obey quantum rules. A quantum computation is therefore not a purely mathematical event floating separate from the world. It is a physical rearrangement of information at one of the deepest levels that current science can handle. This makes the question of where a quantum computation happens more subtle than it first appears. In ordinary computers, the location is simple. A charge sits in a transistor. A magnetic orientation sits in memory. A signal moves along a wire. Information has an address inside a device. But in a quantum system, especially an entangled one, the information can be stored in the correlations throughout the whole system more than in any one part. A pair of entangled qubits can have properties together that neither qubit has on its own. A larger quantum register can contain a global structure that cannot be broken down into independent local parts without losing what makes it quantum. The computation is not sitting neatly in one qubit or another, it is in the joint state. This is what also shows up in black hole physics, because when physicists studied the entropy of black holes, they found that the amount of information associated with a black hole seemed to be linked not to its volume, but to the area of its boundary. This result began with the work of Jacob Bekenstein and Stephen Hawking, and it changed how researchers thought about space itself. In ordinary intuition, a larger volume should contain more possible information, because there is more room inside it. Black holes suggest a different rule. The maximum information in a region can be scaled by the surface that encloses it, not by the space within. This led Gerard Hooft and Leonard Susskind to develop what became known as the holographic principle. This principle does not mean the world is a simple illusion, or a projected image in the ordinary sense. It means that in theories of quantum gravity, the information that describes a region of space can be represented on a lower dimensional boundary. The lesson is not that everyday space is fake. The lesson is that space may be emergent. It may arise from deeper quantum information, rather than existing as the most fundamental container of reality. Entanglement may be particularly important in this process. Some theories suggest that the connectivity of space is related to the patterns of entanglement in an underlying quantum state. When the entanglement changes, the effective geometry can change with it. These ideas are not settled science like atomic theory or electromagnetism, but they are not loose speculation either. They arise from black hole thermodynamics, quantum field theory, and mathematical models that have produced powerful insights. And this matters for quantum computation because the machines manipulate exactly the kind of information that seems central in these deeper theories. A processor with entangled qubits is not bending space or opening a visible gateway to another place. It is doing something more modest and more precise. It is controlling quantum information in a form where location and separation are not the primary facts, and that is already enough to make the technology significant. It puts human engineering in contact with the same conceptual layer that physicists are exploring when they ask what black holes remember, why entropy has boundaries, and how space-time might emerge. Seth Lloyd, a physicist at the Massachusetts Institute of Technology, has described the universe itself as a kind of quantum information processing system. In this view, every interaction between physical systems can be understood as a process that transforms information. Particles collide, fields evolve, atoms bind and separate, and in each case, the state of the universe changes according to the rules. This does not require imagining the universe as a machine built by someone, or a program in the ordinary human sense. It is a way of saying that computation and physical evolution are not entirely separate ideas. A computer is a physical system arranged so that its evolution has a useful interpretation. The universe is the larger physical system, whose evolution gives rise to every possible useful interpretation. Therefore, quantum computers are special, because they are deliberately arranged to use the rules the universe has been using all along, without needing human design. When a molecule changes shape, when electrons occupy energy levels, when light interacts with matter, quantum information is transformed. These new machines are attempts to steer such transformations toward chosen answers. This is why the phrase information beneath matter must be used carefully. It does not mean matter is not real. Matter is very real at the level where bodies, planets, instruments, and labs exist. It means the stability of matter may depend on patterns of quantum information that are more fundamental than the solid objects they produce. An atom is not a little classical ball. It is a structured quantum system. A chemical bond is not a miniature hook. It is an arrangement of quantum states. Quantum computers take this fact and make it operational. What is unsettling is not that this makes reality less real. It is the fact that reality is less like the simple picture, built from definite objects with definite properties that exist independent of how information is arranged. At the bottom, what can be known, what can be stored, what can remain coherent, and what can be erased are not secondary questions. They are part of the physical fabric. The classical world stays fixed because information about it is constantly being recorded and shared by the environment. The quantum world stays powerful when information is protected from that sharing, and black holes suggest that information can limit what space can contain. Holographic models suggest that geometry itself can emerge from more fundamental quantum relationships. Quantum computers stand inside this great shift, and if quantum-level information is not limited to artificial machines, then nature may have learned to use it long ago, and then the search moves away from cold labs and turns toward leaves, proteins, cells, and living bodies, and therefore, the question of the mind enters the story where certainty thins, because the quantum effects in photosynthesis, magnetoreception, and enzyme chemistry are difficult enough, but they relate to specific molecular tasks. Consciousness is different. It is not a reaction, it is not an energy transfer, or a navigational cue. It is the existence of experience itself. Modern neuroscience has mapped many of the structures associated with awareness, but a full explanation for why physical activity in the brain should be accompanied by subjective experience remains elusive. Most researchers approach the problem through classical biology. Neurons receive signals, change their electrical states, release neurotransmitters, and participate in networks whose patterns correlate with perception, decision, and memory. But is this picture complete? The mathematical physicist Roger Penrose and the anesthesiologist Stuart Hameroff have argued that it is not. Their proposal, known as orchestrated objective reduction, places the central process of consciousness inside microtubules. Microtubules are abundant, especially in neurons, where they contribute to transport, structure, and cellular dynamics. Penrose and Hameroff suggested that quantum states within these structures could become organized in a way that then undergoes a physical reduction, producing the discrete moments of conscious experience. This claim was daring for two reasons. First, it suggested that consciousness depends on quantum physics in a special way, not just on the ordinary quantum chemistry that underlies all matter. Second, it suggested that the reduction of a quantum state might be an objective physical event linked to gravity, not just an update in information or an ordinary process of environmental decoherence. This is far outside the standard view. Therefore, it faced strong criticism. The brain is warm, wet, chemically active, and noisy. These are the conditions that normally destroy fragile quantum coherence. In the year 2000, dilution. Max Tegmark calculated that the kind of quantum states proposed for microtubules would decohere far too quickly to influence neural processing. His argument became one of the main reasons many scientists dismissed the theory. If coherence dies long before a neuron can fire or a conscious moment can form, then it cannot play the proposed role. Penrose and Hameroff have disputed some of the assumptions behind these calculations, but for years, the wider field remained skeptical. The theory also faced a broader problem. Even if quantum effects did occur in microtubules, showing that they were necessary for consciousness is much harder than showing they exist. A real explanation would have to connect quantum events to neural computation, brain dynamics, anesthesia, cognition, and subjective experience with testable predictions. This standard has not yet been met in a way that convinces most neuroscientists. At the same time, the theory has not disappeared. It has persisted, partly because some new evidence has made the old dismissal seem less secure. Research on quantum biology has shown that warm biological environments are not automatically hostile to all useful quantum behavior. Certain molecular structures can preserve coherence for long enough for specific tasks, and studies on microtubules and their component proteins have suggested they could support collective electromagnetic or quantum-related behavior under some conditions. These findings do not prove orchestrated objective reduction, but they do show that the simple argument that biology is too warm for any relevant quantum process is no longer sufficient on its own. The serious position is a careful one. Quantum effects in the brain are possible in some way, because the brain is made of quantum matter. The harder question is whether any such effect is coherent, preserved, functionally important, and specifically tied to awareness. Therefore, if consciousness is entirely classical in a working sense, then the relationship with artificial quantum machines would be indirect. But if a quantum process does play a central role, the boundary changes. The brain would not be a quantum computer in the same sense as a programmable processor made of qubits and gates. It would be a biological system in which quantum events contribute to the formation or organization of experience. Calling the brain a quantum computer too casually can hide more than it reveals. A lab quantum computer is built to solve specific computational problems through controlled superposition, entanglement, interference, and measurement. A brain is an evolved organ enmeshed in the workings of metabolism, emotion, memory, perception, bodily regulation, and social behavior. Even if microtubules used quantum effects, the brain is not running Shor's algorithm during a thought. It is doing something biological, embedded in living tissue. Yet, the comparison becomes meaningful at deeper level. Both systems would be using quantum information in ways that are not fully reducible to ordinary classical bits. Both would depend on delicate physical states, where timing and environment matter, and both would force the question of whether information processing and physical reality are more closely linked than older machine metaphors allowed. The many worlds interpretation adds another difficult dimension. In Everett's view, measurement outcomes correspond to branches of the universal wave function. If a central process in consciousness involves quantum events, then some thinkers have suggested that conscious histories might also branch along with those events. This idea is striking, but it is not settled neuroscience. It depends on both a controversial interpretation of quantum mechanics and a controversial theory of consciousness. The better way to phrase it is conditional. If quantum events are central to conscious moments, and if Everett's reading of quantum mechanics is correct, then personal identity might be less like a single unbroken line and more like a set of constantly diverging histories, or a projected image in the ordinary sense. It means that in theories of quantum gravity, the information that describes a region of space can be represented on a lower dimensional boundary. The lesson is not that everyday space is fake. The lesson is that space may be emergent. It may arise from deeper quantum information, rather than existing as the most fundamental container of reality. Entanglement may be particularly important in this process. Some theories suggest that the connectivity of space is related to the patterns of entanglement in an underlying quantum state. When the entanglement changes, the effective geometry can change with it. These ideas are not settled science like atomic theory or electromagnetism, but they are not loose speculation either. They arise from black hole thermodynamics, quantum field theory, and mathematical models that have produced powerful insights. And this matters for quantum computation, because the machines manipulate exactly the kind of information that seems central in these deeper theories. A processor with entangled qubits is not bending space or opening a visible gateway to another place. It is doing something more modest and more precise. It is controlling quantum information in a form where location and separation are not the primary facts, and that is already enough to make the technology significant. It puts human engineering in contact with the same conceptual layer that physicists are exploring when they ask what black holes remember, why entropy has boundaries, and how space-time might emerge. Seth Lloyd, a physicist at the Massachusetts Institute of Technology, has described the universe itself as a kind of quantum information processing system. In this view, every interaction between physical systems can be understood as a process that transforms information. Particles collide, fields evolve, atoms bind and separate, and in each case, the state of the universe changes according to the rules. This does not require imagining the universe as a machine built by someone, or a program in the ordinary human sense. It is a way of saying that computation and physical evolution are not entirely separate ideas. A computer is a physical system arranged so that its evolution has a useful interpretation. The universe is the larger physical system, whose evolution gives rise to every possible useful interpretation. Therefore, quantum computers are special, because they are deliberately arranged to use the rules the universe has been using all along, without needing human design. When a molecule changes shape, when electrons occupy energy levels, when light interacts with matter, quantum information is transformed. These new machines are attempts to steer such transformations toward chosen answers. This is why the phrase information beneath matter must be used carefully. It does not mean matter is not real. Matter is very real at the level where bodies, planets, instruments, and labs exist. It means the stability of matter may depend on patterns of quantum information that are more fundamental than the solid objects they produce. An atom is not a little classical ball, it is a structured quantum system. A chemical bond is not a miniature hook. It is an arrangement of quantum states. Quantum computers take this fact and make it operational. What is unsettling is not that this makes reality less real. It is the fact that reality is less like the simple picture, built from definite objects with definite properties that exist independent of how information is arranged. At the bottom, what can be known, what can be stored, what can remain coherent, and what can be erased are not secondary questions. They are part of the physical fabric. The classical world stays fixed because information about it is constantly being recorded and shared by the environment. The quantum world stays powerful when information is protected from that sharing, and black holes suggest that information can limit what space can contain. Holographic models suggest that geometry itself can emerge from more fundamental quantum relationships. Quantum computers stand inside this great shift, and if quantum-level information is not limited to artificial machines, then nature may have learned to use it long ago, and then the search moves away from cold labs and turns toward leaves, proteins, cells, and living bodies, and therefore, the question of the mind enters the story where certainty thins, because the quantum effects in photosynthesis, magnetoreception, and enzyme chemistry are difficult enough, but they relate to specific molecular tasks. Consciousness is different. It is not a reaction, it is not an energy transfer, or a navigational cue. It is the existence of experience itself. Modern neuroscience has mapped many of the structures associated with awareness, but a full explanation for why physical activity in the brain should be accompanied by subjective experience remains elusive. Most researchers approach the problem through classical biology. Neurons receive signals, change their electrical states, release neurotransmitters, and participate in networks whose patterns correlate with perception, decision, and memory. But is this picture complete? The mathematical physicist Roger Penrose and the anesthesiologist Stuart Hameroff have argued that it is not. Their proposal, known as orchestrated objective reduction, places the central process of consciousness inside microtubules. Microtubules are abundant, especially in neurons, where they contribute to transport, structure, and cellular dynamics. Penrose and Hameroff suggested that quantum states within these structures could become organized in a way that then undergoes a physical reduction, producing the discrete moments of conscious experience. This claim was daring for two reasons. First, it suggested that consciousness depends on quantum physics in a special way, not just on the ordinary quantum chemistry that underlies all matter. Second, it suggested that the reduction of a quantum state might be an objective physical event linked to gravity, not just an update in information or an ordinary process of environmental decoherence. This is far outside the standard view. Therefore, it faced strong criticism. The brain is warm, wet, chemically active, and noisy. These are the conditions that normally destroy fragile quantum coherence. In the year 2000, dilution. Max Tegmark calculated that the kind of quantum states proposed for microtubules would decohere far too quickly to influence neural processing. His argument became one of the main reasons many scientists dismissed the theory. If coherence dies long before a neuron can fire or a conscious moment can form, then it cannot play the proposed role. Penrose and Hameroff have disputed some of the assumptions behind these calculations, but for years, the wider field remained skeptical. The theory also faced a broader problem. Even if quantum effects did occur in microtubules, showing that they were necessary for consciousness is much harder than showing they exist. A real explanation would have to connect quantum events to neural computation, brain dynamics, anesthesia, cognition, and subjective experience with testable predictions. This standard has not yet been met in a way that convinces most neuroscientists. At the same time, the theory has not disappeared. It has persisted, partly because some new evidence has made the old dismissal seem less secure. Research on quantum biology has shown that warm biological environments are not automatically hostile to all useful quantum behavior. Certain molecular structures can preserve coherence for long enough for specific tasks, and studies on microtubules and their component proteins have suggested they could support collective electromagnetic or quantum-related behavior under some conditions. These findings do not prove orchestrated objective reduction, but they do show that the simple argument that biology is too warm for any relevant quantum process is no longer sufficient on its own. The serious position is a careful one. Quantum effects in the brain are possible in some way, because the brain is made of quantum matter. The harder question is whether any such effect is coherent, preserved, functionally important, and specifically tied to awareness. Therefore, if consciousness is entirely classical in a working sense, then the relationship with artificial quantum machines would be indirect. But if a quantum process does play a central role, the boundary changes. The brain would not be a quantum computer in the same sense as a programmable processor made of qubits and gates. It would be a biological system in which quantum events contribute to the formation or organization of experience. Calling the brain a quantum computer too casually can hide more than it reveals. A lab quantum computer is built to solve specific computational problems through controlled superposition, entanglement, interference, and measurement. A brain is an evolved organ enmeshed in the workings of metabolism, emotion, memory, perception, bodily regulation, and social behavior. Even if microtubules used quantum effects, the brain is not running Shor's algorithm during a thought. It is doing something biological, embedded in living tissue. Yet, the comparison becomes meaningful at deeper level. Both systems would be using quantum information in ways that are not fully reducible to ordinary classical bits. Both would depend on delicate physical states, where timing and environment matter, and both would force the question of whether information processing and physical reality are more closely linked than older machine metaphors allowed. The many worlds interpretation adds another difficult dimension. In Everett's view, measurement outcomes correspond to branches of the universal wave function. If a central process in consciousness involves quantum events, then some thinkers have suggested that conscious histories might also branch along with those events. This idea is striking, but it is not settled neuroscience. It depends on both a controversial interpretation of quantum mechanics and a controversial theory of consciousness. The better way to phrase it is conditional. If quantum events are central to conscious moments, and if Everett's reading of quantum mechanics is correct, then personal identity might be less like a single unbroken line and more like a set of constantly diverging histories. This does not mean that ordinary choice becomes meaningless. It does not mean a person can communicate with alternate branches. It does not prove that imagined lives exist in a physically reachable place. It means that the physical basis of experience, if it is quantum at its core, may depend on the same unresolved structure that quantum computers reveal. What is unsettling is not a dramatic vision of copies. It is the quieter recognition that the foundations of the self may depend on processes that are still not understood. Any familiar sense of identity feels stable from the inside, because memory, body, and environment hold it together. But beneath that stability, the physical world does not behave like a collection of fixed classical parts. It behaves according to quantum rules, and the mind, whatever else it is, must emerge within this world. That fact alone is enough to make the old separation between physics and inner experience feel less secure. Penrose and Hameroff could be partly right, mostly wrong, or pointing to a question that will eventually be answered in a different language. The field has not settled this, but now it is time to pause and reflect, because these machines might not just be shaking up science, but the very thing that makes us, our sense of self. So what do all these findings mean for us, for our place in this universe? Because this is not just a technology race, it is also a search for identity. And so now we ask ourselves, what does all this technology, all this competition, mean? The arms race accelerates at the moment when the question of whether quantum computation is possible stops and turns into the question of how quickly it can be made reliable, scalable, and useful. Because, for a long time, the field moved forward with important but limited demonstrations. A few qubits could be controlled, then more qubits, then simple algorithms, then noisy processors offered through cloud platforms, where researchers could test circuits on real hardware and learn how errors behave outside of ideal theory. These were necessary steps, but they belong to an early phase. The new phase is different. It is not defined just by qubit count, or a single dramatic benchmark, or a company announcing a larger chip. It is defined by the convergence of many efforts toward fault tolerance, the state where a quantum computer can keep working even if every physical component remains imperfect. Therefore, this is the real goal. A noisy quantum processor can demonstrate physics, test methods, and sometimes outperform classical imitation on carefully chosen tasks. But a fault-tolerant quantum computer can run long computations that correct errors faster than they accumulate. The difference is immense. It is the difference between a fragile lab demonstration and a machine that could become part of the computational infrastructure of civilization. This is why governments, universities, startups, established technology companies, cloud providers, defense agencies, and cryptography groups are all watching the same milestones. The race is not just to build more qubits, it is to build qubits that can be controlled, connected, corrected, fabricated, and replicated at scale. Superconducting processors remain one of the most visible paths. They use tiny circuits cooled to extremely low temperatures, where electrical behavior can be made quantum and controlled with microwave pulses. Their advantages are speed and a strong connection to existing fabrication methods. Their challenges are that they require demanding cryogenic systems and must battle many sources of noise in solid materials. Google's work after Sycamore has focused heavily on error correction, especially on showing that larger error-correcting codes can reduce logical error rather than just adding complexity. IBM has pursued larger chips, better connectivity layouts, improved software tools, and roadmaps that aim to reach useful quantum advantage before full fault tolerance. Progress in this architecture depends on many details at once: cleaner materials, sharper calibration, faster feedback, better control electronics, and codes that can detect errors without destroying the information they protect. A superconducting chip may look like a small fabricated object, but the full computer includes the entire cold environment built around it. Scaling the chip also means scaling the refrigerator, the wiring, the control signals, and the classical systems that direct and interpret the quantum operations. Trapped ion systems take a different route. Their qubits are single-charged atoms held in electromagnetic fields. Because the atoms of the same isotope are naturally identical, trapped ion qubits can have excellent uniformity and long coherence times. Lasers prepare, manipulate, and read out their states. The precision can be remarkable. The challenge is speed, integration, and scale. A small chain of ions can be controlled with high fidelity, but building a very large machine requires figuring out how to move ions, connect separate traps, deliver many laser signals, and maintain stability across a growing architecture. Companies like IonQ and Continuum have worked to turn trapped ion strengths into commercial systems, while researchers explore modular interconnects that would allow separate processors to be linked via photons. This modular idea is important because it changes the image of scale. A future quantum computer might not be a single giant chip. It might be a network of smaller quantum processors linked by quantum connections, with entanglement shared between modules. This resembles how classical computing grew from single processors to data centers, though the physics is far more delicate. Neutral atom processors offer another path. They use arrays of atoms held in place by light, arranged in reconfigurable patterns. These systems are attractive because large arrays can be created, and interactions between the atoms can be turned on through highly excited states called Rydberg states. Photonic quantum computation tries to build with light itself, using photons as the carriers of quantum information. Photons are naturally mobile and resistant to some kinds of noise, making them attractive for communication and networking. The challenge is to make the photons interact strongly enough to perform gates, or to arrange measurement-based schemes where entanglement and detection together produce a computation. Silicon spin qubits seek compatibility with the manufacturing knowledge of the semiconductor industry. By using the quantum states of electrons or nuclei in carefully engineered silicon devices, their promise is compactness and potential manufacturability. And topological approaches aim for something more unusual: to store information in the global properties of exotic states of matter, so that local noise has less power to corrupt it. Each path has a different personality, but none is easy. The fact that so many remain active tells its own story. Nobody yet knows which architecture, or which combination of architectures, will dominate in the mature era. The arms race is therefore not a single race on a single track. It is a landscape of competing physical bets. The classical computing companies are crucial. Because quantum processors will not run on their own. They need classical control systems to send the pulses, process the measurement results, update the calibrations, decode the errors, and connect users to the machine. A future quantum computer will likely be a hybrid system, where the quantum hardware performs the parts of a task suited to quantum evolution, and classical computers handle the preparation, correction, data movement, and interpretation. National competition adds another layer. Quantum computation has consequences for chemistry, materials, logistics, finance, communications, and national security. It could affect cryptography. It could improve sensors. It could help simulate molecules relevant to energy storage, fertilizer production, carbon capture, and medicine. This is why governments treat quantum technology as strategic infrastructure. Public funding supports research centers, training programs, domestic supply chains, and international partnerships. But in the middle of all this racing, there is a fact that gets overlooked. These machines don't just promise better science, they also threaten the very systems that keep modern secrets safe. And when that day comes, everything will change silently. Because the day cryptography breaks will not begin with a loud bang, and therefore, the day cryptography breaks will begin silently. Because as cryptography usually does its work by not being noticed, it is the background assurance that a message sent over a hostile network cannot be read by anyone but the intended recipient. It protects passwords, medical records, financial transfers, military orders, software updates, and private photos. Much of this protection relies on mathematical problems that are easy to create in one direction, but extremely difficult to reverse in the other. Multiplying two large prime numbers is simple for a computer. But taking that giant product and finding the two primes that formed it is much harder. Classical cryptography does not rely on a problem being impossible in an absolute sense. It relies on the cost of solving it being so high that no attacker should be able to afford the time, energy, or machinery required. But quantum computation changes what that cost means for some of the most important public key systems. The turning point came when Peter Shor showed that a capable enough quantum computer could factor large numbers and solve related discrete logarithm problems far more efficiently than the best-known classical methods. The algorithm did not break the encryption by guessing faster. It changed the problem. It converted the hidden structure inside the numbers into a form that quantum interference could reveal. For systems like RSA and elliptic curve cryptography, this is profoundly important. These systems are used to exchange keys, verify identities, and protect the start of a secure communication. When the public key is known, the private key is supposed to remain effectively unreachable. Shor's algorithm says that with a large enough vertical bar fault-tolerant quantum computer vertical bar, the private key could become reachable. The phrase "large enough" carries most of the practical uncertainty, because today's quantum processors cannot run Shor's algorithm at the scale required against modern cryptography. They have too few reliable logical qubits, too much noise, and not enough depth of error correction for such an attack. But cryptography has to think ahead. A code that is secure only until a machine is built may already be insecure for information that needs to stay secret for decades. This is the reason for the strategy known as harvest now, decrypt later. An attacker does not need a quantum computer today to do damage in the future. The attacker can harvest encrypted traffic today, store it, and wait. Diplomatic cables, intelligence files, genetic records, legal documents, and industrial designs can all retain their value long after they were transmitted. If a quantum computer capable of breaking the relevant public key encryption becomes available in the future, the old captured data could be opened. The theft would have happened years ago, but the reading would happen later. Therefore, this delayed threat makes the transition urgent, even before the machine exists. The most vulnerable information is not the message that needs to stay private for a week. It is the message that needs to stay private for a lifetime. A medical record, a source identity, a long-term government secret, or a design for critical infrastructure can all have a security horizon longer than the expected timeline for powerful quantum machines. This is why the cryptography community has been preparing for what is often called post-quantum cryptography. This name does not mean cryptography used after quantum computers have broken everything. It means cryptography designed to resist attack from both classical and quantum computers. The US standards, body, NIST, has run a long public process to evaluate and standardize new algorithms. Many of these algorithms are based on mathematical problems not known to be efficiently solvable with quantum methods, such as lattice-based problems, hash-based signatures, code-based cryptography, and multivariate structures. But the transition is difficult, because as cryptography is everywhere. It is built into web browsers, payment systems, messaging apps, virtual private networks, satellites, embedded devices, passports, smart cards, industrial controllers, cloud infrastructure, and the update mechanisms that keep software trustworthy. Changing the algorithms is not like changing one lock on one door. It is more like changing a vast network of locks while the building remains occupied and the doors must keep opening for the right people. Old devices may not have enough memory or processing power for new algorithms. Some systems are hard to update. Some are forgotten until they fail. Even when the standards exist, deployment can take many years. In the meantime, systems may need hybrid approaches that use both classical and post-quantum methods together, so that an attacker would have to defeat both. Symmetric cryptography faces a different situation. Algorithms like AES are not broken by Shor's algorithm, because they are not based on factoring or discrete logarithms. Grover's algorithm could provide a quadratic speed-up for a brute force search, which means key lengths may need to be larger to maintain the same level of security. This is serious, but more manageable. Doubling the key sizes can often restore the security against this kind of quantum search. Digital signatures deserve special attention, because they do more than hide information. They prove that software, messages, certificates, and transactions came from their claimed source. If signature schemes become forgeable, attackers could impersonate trusted authorities, sign malicious updates, or undermine the chain of trust that holds digital systems together. The danger is therefore not just that old secrets could be read, it is that future trust could be faked if the migration happens too late. This is what gives Q-Day its weight. Q-Day does not have to be the day a quantum computer is publicly announced. It could be the day one exists in a private lab, a national program, or a restricted facility, able to run attacks before the wider world knows. The calm view is that nobody should see this as the instant collapse of digital civilization. The equally calm view is that waiting for proof of disaster would be poor security. But there is one more question. Do these machines only exist to break and destroy? Or could that same incredible power also be used to repair, to heal, and even to cure? And therefore, the medicine from the impossible simulation starts with a simple limitation. Because the body is made of molecules, and molecules obey quantum mechanics. Every bond, like a fold, reaction, and charge transfer depends on electrons arranged in quantum states. Yet, the full quantum behavior of even a modest molecule can be too complex for classical computers to calculate exactly. Chemists and biologists have learned to get around this problem with approximations. They use models that treat some parts of a molecule in detail and other parts more crudely. But these approximations have limits. Proteins are flexible. Water changes the energy landscape around them. A drug molecule might bind strongly in one way and weakly in another. In many cases, the most important event is not the stable molecule you can draw on a page, but the fleeting quantum rearrangement that happens as one chemical state turns into another. Therefore, this is the problem that quantum simulation is meant to address. A quantum system is hard to simulate with a classical machine, because its state contains amplitudes and correlations that can grow beyond practical storage. A quantum computer, if it can be made reliable enough, could represent some of these states more naturally. It would not have to force the molecule into a classical description at every step. It could use qubits to directly model the quantum relationships, letting the simulated system evolve under rules that are close to the rules that govern the real molecule. This does not mean that future quantum computers will instantly solve biology. Cells are not just quantum systems. They are also thermal, is noisy, fluid, and crowded. A disease is not a single equation. It is a pattern involving genes, proteins, tissues, immune responses, environment, age, and history. Yet, at the molecular level where drugs bind and reactions happen, improved quantum simulation could be extremely valuable because drug discovery often starts with the search for molecules that interact with a biological target, like an enzyme, a receptor, or a viral protein. The target has a shape, but it also has charge distributions, mobile side chains, hidden pockets, and water molecules that can help or hinder binding. A candidate drug has to fit not just geometrically, but energetically. It must bind strongly enough, avoid binding where it shouldn't, remain stable in the body, dissolve properly, cross barriers, and be cleared safely. Every requirement depends on molecular interactions. Better simulation could reduce the number of failed candidates by showing earlier which interactions are physically plausible. One particularly important area is enzyme chemistry. Enzymes make life possible by lowering the energy required for reactions. Therefore, designing a drug to affect an enzyme requires understanding the reaction pathway, especially the transition state where bonds are partly broken and partly formed. Transition states are quantum mechanical objects in the deepest sense. They involve electron rearrangement, tunneling in some cases, and subtle energy differences. If a quantum computer could accurately model these states for medically important enzymes, it could guide the design of inhibitors that mimic the transition state or stabilize a desired reaction path. This would not replace experiments, it would make experiments more focused. Protein folding is another area often mentioned in connection with quantum computation. Artificial intelligence systems have already transformed the prediction of many protein structures from their amino acid sequences. This is a huge success for classical computation and data-driven learning. Quantum computers would not need to do what those systems already do well. The remaining challenges are more specific. Proteins are not static sculptures. They move. They switch between conformations. Some diseases involve misfolded proteins that aggregate into harmful structures. Others involve subtle changes in dynamics rather than a single wrong shape. Quantum simulation could help where the electronic structure, chemical reactivity, or subtle energy differences are central to the biological behavior. The likely future is hybrid, not purely quantum. Classical machines will still manage large data sets, biological networks, and broad searches. Quantum processors could be called upon for the parts of a computation where quantum mechanics is the main event, not a nuisance. Material science could benefit similarly, and medicine relies heavily on materials. Better batteries support medical devices and hospital resilience. Improved catalysts can produce drugs with less waste. New sensors could detect biomarkers earlier, and materials for implants, imaging, filtration, and drug delivery all depend on molecular and electronic behavior. Quantum simulation could help design catalysts for cleaner chemical production, including the synthesis of pharmaceutical compounds. These applications may sound less dramatic than breaking cryptography, but they may be more humane in their long-term consequences. A machine that can reveal secrets can also reveal how electrons move through a catalyst, how a molecule binds inside a protein, or how a material conducts charge. The moral direction is not built into the physics. It is chosen by the society that develops and uses the tool, but there are also reasons to be careful. Many claims about quantum advantage in medicine are still early. Simulating a real drug in a real protein to a clinically useful accuracy is far beyond most current hardware. Therefore, the deeper promise is not just speed, it is fidelity to the level of nature where chemistry actually happens. Classical models often succeed by simplifying. Quantum simulation could succeed, at least where simplification is a barrier, by simplifying less. This is why the medical promise of quantum computation feels different from its cryptographic threat. Cryptography is vulnerable because certain mathematical structures become easier to reverse. Medicine is hopeful because certain physical structures could become easier to understand. One breaks a protective assumption, the other could repair an explanatory gap. Both depend on the same controlled manipulation of quantum information. So the same technology carries two futures at once. It could make old protections weaker and new treatments more reachable. It could undermine security while empowering science. It could turn hidden mathematical structure into risk and hidden molecular structure into knowledge. The balance between these futures will depend on preparation, regulation, funding, openness, and restraint. Because the cold machine does not decide whether its computations are used to read archived secrets or to design better drugs. It just makes certain computations, once unreachable, possible. But, in the middle of all this scientific and technological revolution, the question of the door still stands unanswered, and therefore the door question remains, after the machines, the biology, the cryptography, and the medicine are all put back into one frame. Because us quantum computers do not prove that reality contains many worlds, they do not prove that consciousness survives in other branches, or that information can travel from one history to another after decoherence has separated them. The most careful science does not permit those conclusions. What the machines do prove is narrower and still profound. You can prepare a physical system so that several possible components of its quantum state remain coherent for long enough to interfere with one another. These components can interfere, and that interference can shape the answer later seen in a classical measurement. This is not an ordinary hidden process. This is a kind of physical evolution that forces every interpretation of quantum mechanics to account for the same fact. Before the result emerges, something is happening that is real enough to be engineered. Therefore, the disagreement is over what this something means. In the Everettian picture, the answer is direct. The wave function describes reality as a whole, and the different terms within it correspond to branches that are all physically real. A quantum computer works because it maintains controlled relationships between these branches, before they have separated too far to interfere. In this view, the computation is not borrowing a metaphor from the multiverse. It is using the structure of the multiverse at a moment when the branches are still mathematically close enough to interfere. This is David Deutsch's strongest claim, and the reason why quantum computation is important to him, not just as technology, but as evidence about the architecture of existence. Many physicists disagree or avoid judgment. because other interpretations can reproduce the same predictions without treating every branch as equally real. Yet, the Everettian view has a certain clarity. Therefore, the central question becomes whether quantum computers are doors in any meaningful sense. A door implies passage, and the known physics is cautious here. Interference can only happen as long as coherence is preserved. When a system decoheres, information about its alternatives has spread into the environment in a pattern of extremely complex correlations. The branches no longer have a usable interference with each other. In the many worlds view, they have not vanished, but they have become mutually inaccessible. A quantum computer does not open a gateway to a mature branch where another version of events has already unfolded. It holds a small system coherent before this separation has become irreversible for practical purposes. The computation is possible because the branching has not yet become ordinary classical history. This distinction removes much of the unnecessary fear, because the machine is not a tunnel through which messages pass from other lives. It is a controlled quantum system where amplitudes are allowed to combine. Before measurement fixes the outcome available here, the door, if the word is to be used, is not a passage between finished worlds. It is a brief region where the alternatives have not yet become fully separate records. This also changes how quantum immortality should be understood. The idea comes up in some discussions of many worlds and personal identity. In its simplest form, it suggests that if every quantum outcome occurs, then there may always be branches in which a conscious observer continues, even after events that would end life in other branches. This is a thought experiment, not a settled science. It is not proof that death can be outrun, and it should never be seen as a reason to dismiss harm, grief, or biological reality. The living body remains vulnerable, as far as can be responsibly said by science. Conscious experience depends on the functioning brain and body in the branch one inhabits. The other branches, if they exist, are not contactable from here, not verifiable, and not usable as a shield against consequence. The value of the thought experiment is not comfort. It is that it reveals how strange personal identity becomes if the wave function is taken to be fully real. If history branches, then the word I may refer not to a single line, but to a pattern that can split into non-communicating continuities. From inside any one continuity, experience remains singular. Memory gives it a past. The body gives it a location. The environment gives it stable records. There is no felt multiplicity, because each branch contains its own integrated observer. What is unsettling is not that daily life becomes unreal. It is that the singularity of experience might be local, rather than universal. Artificial intelligence adds another recent layer to the same problem. Classical AI already processes information in ways too complex for any one individual to fully oversee. If future artificial systems are connected to quantum processes, they could design circuits, discover algorithms, optimize error correction, and interpret quantum outputs with less direct human guidance. This does not mean a quantum computer becomes conscious, or that an artificial system gains access to other branches. Those claims go far beyond current evidence. The more realistic issue is that machines could become better than humans at using the parts of quantum theory that humans understand mathematically, but cannot picture intuitively. Therefore, the most important door may be an epistemic one, a door in knowledge rather than in space. Quantum computers allow science to enter a regime where questions that were once treated as philosophical become testable engineering constraints. How long can coherence be preserved? How many errors can be corrected? Which problems allow for useful interference? Which simulations match experiments? These questions do not remove the mystery, they give it structure. The old measurement debate no longer lives just in seminars and books. It is being cooled, cabled, calibrated, and measured in labs. Every advance in control makes the unseen part of the theory more operational. Every failure shows how powerfully the classical world reasserts itself through decoherence. The machine becomes a disciplined meeting point between what can be built and what is hard to understand. If many worlds is right, then quantum computers may be the first devices deliberately designed to let neighboring components of the universal wave function influence an answer before they become inaccessible. And now we know reality is not made less real by quantum theory, but it is made less familiar. The ordinary world remains the place where bodies live, records last, drugs work, and consequences unfold. It is the stable branch of experience, sustained by decoherence and shared information. But beneath that stability, quantum physics continues to describe a wider set of possibilities than ordinary perception can hold, and now, as the journey ends, a single image remains in our minds. In this video, we saw how quantum machines reveal the deepest layer of reality. But I didn't tell you one thing. The entire story of the universe was written in just the first 3 minutes. Every atom, every star, every galaxy was born in that fleeting moment. On our next journey,